Okay, sir. In the last class, you proved a theorem, which was in the lines of if we are given a group G and it can be written down as as the product of two normal subgroups
Yeah.
and the intersection being trivial,
Hmm.
then then there exists an isomorphism between
Hmm.
G and the direct product between the two groups.
Yeah.
So, yeah, so what I can what I think is when we are doing the map from G to N1 cross
Hmm.
N2, we are essentially breaking it down into G to N1 N2 and then from N1 N2 to N1 cross N2.
Yeah.
So that we want to prove the isomorphism between G to N1 cross N2, we have to show that both G to N1 N2 is isomorphic as well as N1 N2 to N1 cross N2 is isomorphic. So,
Uh, I'm
so
not sure
what
whether
in the class?
I'm getting your point. Uh, After all, are you saying G to N1%? Okay, let me just try writing down what you are saying so that I can sort of follow. And this is where the new thing comes in. Let's see. Let's hope. So, okay,
Uh,
pretty auspicious beginning anyway. But now, what you are saying something is something like
uh,
this. Are you saying G? What we wanted to show is G is isomorphic to N1
yeah,
direct product N2, right? So we wanted to show that
yeah.
there's an
Uh,
isomorphism between them. So what we
mm,
have is, I find that my seat is too low for this. Anyway, so we had N1 is a normal subgroup of G, N2 is another normal subgroup
yeah,
of G, and we
yeah,
had N1 intersection into equals just one element, the identity. The identity has to be there anyway, right? Because they are
yeah.
both subgroups, but there is the only one which you have. And finally, your G equals N1, N2. This is important. So if you have
Yes.
all this,
Yeah.
then you can show that G is isomorphic to
Mm.
N1 direct product N2. Okay, so what we showed was, uh, okay, so
Mm.
is your problem with the proof or is your problem with this theorem itself?
No, no problem. With the proof, like it's not a problem. So what I think is happening is you're making making a map go from G to N1
Mm-hmm.
N2 and then from N1 N2 to N1 cross N2. So you're making you're composing two maps and making the final map which is G to N1 cross N2.
Yeah, we
So
what
to
we
prove G,
yeah what we do need is a map from G to N1 cross N2, right? And the way we did that was essentially say
yeah,
that every element G, as long as G belongs to capital G, then G can be written, of course, as N1 N2. There's no problem about that because that's what G equal to N1 N2 means, right? When you say G equals
yeah,
N1 N2, that exactly means that every element of the group G, capital G, can be written down as an element product of an element of N1. So where N1 of course belongs to capital N1 and N2 belongs to capital N2. This is exactly what the product, G being the product, means. So that's not an issue. That in itself is okay.
yes,
Okay.
yeah,
So what we actually
mm,
showed on top of that is
mm,
that this is unique in the sense that if G is both N1 N2 and N1 prime N2 prime with the same restrictions that N1 and N2 belong to
yes,
capital N1 capital N2, N1 prime N2 prime belongs to capital N1 capital N2 respectively,
yes,
then N1 must be equal to N1 prime and N2 must be equal to N2 prime.
yeah,
For this, we did not need the fact that capital N1 and
yes.
capital N2 are normal subgroups. All we needed was the intersection of N1 and N2 is the identity alone. Okay. So what this helped us to do,
Huh.
yeah.
So
Then,
yeah, so over here, you're essentially showing that the map G to N1, N2 is a 1-1 map and it's an on-to
Yeah,
map. But we also have to show that this is a homomorphism, right?
not really.
Because we want to make the
Not really. First of all, N1, N2 is not even a G is N1, N2, right? There is no, there is not a distinct group. Okay, we are not even trying to show that there is a homomorphism between G and G. Okay, all we are trying to establish here is that for every G, this map G maps to N1 comma N2 is a map which takes you from capital G. Okay, so this particular map, let's call this whatever, let's call this phi. This map maps small g into a pair of elements, and this map actually has a domain of capital G and a codomain of N1 direct product N2, right? Because the result is an ordered pair, right? That's what we did.
Hello.
Hello, can you hear me?
Sir, my network it got hampered. I couldn't.
Okay, what I was saying is
last 30 seconds.
What I was saying is G maps to, so what we have defined here is a map phi from capital G to N1 cross N2 directly. There's no N1, N2 involved in between. Remember, N1, N2 is nothing but G itself. What we are saying, so what are elements of N1 cross N2? Elements of N1 direct product N2 are ordered pairs, right?
Yes.
Now, using the fact that every G can be uniquely written in the form N1 times N2, I can always define this map that small g maps to this thing. Let me just try highlighting this. This is what I'm saying here. You take small g, you map this to N1, N2. Okay?
Yes.
So this is a map which I have defined from capital G to N1 direct product N2. Is it okay?
Yeah.
And in this map, the only ingredient that went in is the fact that N1 and N2 are unique. So this is a well-defined map. Okay, so the previous argument.
Yes.
So this helped us to define the map properly. And this is a properly well-defined map. Given any G, you can always find one and only one pair N1, N2. Right? Okay, let me just do one thing. Let me shut my camera off because that's eating up the bandwidth a lot. You really don't need to see my face as such. Okay. So this is basically what we did here. We defined the map. Now we have to show that this map is a homomorphism. Okay. So there are two stages up here. One is defining the map properly, and the next is showing this map, which is a map not from G to N1, N2, N2. It's a map from G to N1 cross N2. Right? Because an ordered pair there is an element automatically of the set underlying N1 cross N2. It's an ordered pair that we defined here, right? Okay. And the next part is showing that this is a homomorphism. So that's the next part. In fact, you have to show that this is an isomorphism, which is once you show that is one-to-one onto, and then isomorphism part is straightforward. That's what it did. Of course, straightforward means that's where the normal subgroup nature of the whole thing comes into being. Okay, right?
Okay. Yeah.
So I hope this made this point is cleared up. Okay, so any other questions?
Sir, in the last class when you were talking about point groups, you only took crystal symmetries as the example continuously. So I was just wondering if a point group has to be discrete or can it be continuous like a orthogonal group?
No, look, if you just say that a point group is anything which keeps a point fixed, then the whole orthogonal group, of course, could be part of it.
Yeah,
right? But the context in which we were using it is in the context of symmetries of a crystal.
Okay.
So there, point group and space group are terminologies which are used specifically in solid state theory to describe symmetries of crystals. And there, of course, the point group is not a continuous one; it is a discrete symmetry, right?
Okay.
But of course, in general, and in fact, if you look at the Lorentz transformation to Poincare thing, That's in 4D, right? But in 3D, you could definitely have, say, point group operations, which mean in this case rotations and reflections and inversion, and the translations in 3D. That would also be a symmetry of many theories. In fact, that would be a symmetry of all theories. It's just that because that's nothing but a subset of the entire Poincare symmetries, right?
Okay.
But there are two distinct things. One is the symmetry of a theory, the other is the symmetry of a system. A system may not be symmetric under the same transformations, right? A crystal, for example, although the laws of physics have translation symmetry, a crystal does not have translation symmetry, it has discrete translation symmetry, only a subset of all possible translations, right? The laws of physics may be rotationally invariant. That doesn't mean that any object that you hold in your hand is rotationally invariant. It usually is not, right?
Yes, sir.
So when you apply symmetry laws to figure out properties, sometimes just the laws, the symmetry of the laws is important, but very often you have to pay attention to what kind of symmetry the system you are talking about also has. Okay, anything further? Or shall we start? Have enough people joined yet? Yeah, I think most of you have joined. So, as I said, the only problem is I can't see any chat, so please don't try chatting. If you want to say something, unmute and say. Okay. So last day what we did was, in addition to this direct product, we also talked about the semi-direct product, right? I have to get used to this thing, so there will be some glitches, yeah. But anyway, when we defined the semi-direct product, what we did was we said you have a group G. Oops, I forgot that is the highlighter. Anyway. You have the group G. The other group that you have, okay, I don't remember what I wrote it as, curly I or something. Okay, let's say curly G. I hope I can make out the distinction between capital G and curly G distinctly. But curly G is not just any subgroup, it's a subgroup. It's not just any group, it's a subgroup of the group of automorphisms of G, or a group which is isomorphic to such a subgroup. Remember, very often, at least when we are dealing with group theory, we don't even distinguish between two groups if they are isomorphic to each other, right? So we often say this group is that group, whereas they're only isomorphic to each other, perhaps. So as physical entities, the elements may be very different, but as groups, they are identical. So small g is either a subgroup of odd G or a group which is isomorphic to a subgroup of odd G. Then we defined the semi-direct product, which we wrote as G. Okay, my handwriting is of course going all the way over the place. But of course, small g comes from capital G, alpha comes from this curly G. And the difference between this and the semi-direct product, between the semi-direct product and the direct product turns out to be this one. The composition rule, this part is fine, but G does not compose with G prime directly. G composes with alpha G prime. And we showed several examples. In fact, the point group and the space group example was one of them, which we did not really talk much about, but that's just something you can directly read off from the Poincare versus Lorentz and translation giving the Poincare group example. So I hope we have established that semi-direct products are pretty important things in physics. Many important examples are semi-direct products. But the question really now is, can we prove something similar to the theorem that we just talked about at the beginning of today's class, the one which we discussed the other day? Remember, there what we were really doing was doing this two ways. Suppose we had two groups G1 and G2. We could use them to form the direct product and then show that G1 is a normal subgroup of G1 cross G2. So is G2. Strictly speaking, both of these statements are wrong. Why? Because G1 is not a subset of G1 cross G2, right? G1 has only elements of its own, G1 cross G2 has pairs. One element from G1, the other element from G2. But of course, what we are saying here is G1 is actually isomorphic to G1, let's call it G1 tilde. But the isomorphism simply is this map, small g1 maps to small g1 cross e2, comma e2. So just because we don't distinguish between a group and its isomorphic partner, we are saying G1 and G2 are normal subgroups of G1 cross G2. So that's the way the original components of a direct product go into the full direct product. So that's figuring out the direct product in the straight or direct manner. But what we did in the theorem was work backwards. Suppose I have a group. Can I write that as, so I already have the group. It's not that I have two groups and I have taken the direct product to get this new group. I already have a group. The question was, can I actually use the technique? Can I actually figure out from the group structure itself whether this group can be written down as a direct product? And the answer there was, you have to find out two normal subgroups N1 and N2 such that N1 and N2 are nearly disjoint or as disjoint as they can be, right? Because two subgroups, by virtue of being subgroups, must have at least the identity in common. And the product as sets must be G itself. Then you could show that G is essentially N1 cross N2 or isomorphic to N1 cross N2, to be more precise. The question now is, can we prove something very similar for a semi-direct product? So here, the thing works this way. Suppose given a group G, so that's the question we are asking. Can we write it as a semi-direct product of its subgroups? So we are essentially asking for an analogous theorem to the one that we already had. So here our starting goes this way. H is a subgroup of G, let's say. And N is a normal subgroup of G, such that well, very similarly to what we had before, E and we need one more condition here. I'm going to specify what that condition is soon. Then G is isomorphic to N semi-direct product H. So you can see this theorem that I have stated here is nearly identical to the theorem that we proved the other day. The only distinction was there, instead of H being a subgroup and N being a normal subgroup, we had two normal subgroups, N1 and N2. But the other conditions look the same, right? There if we had N1 intersection N2 is the identity. Here we have N intersection H is the identity. There we had N1 N2 equals G. Here we have NH equals G. Everything, but we have one extra condition which we did not write down, and that condition is a condition about the subgroup H, which is this. I hope everybody knows what Z of H is. Yes?
No, sir. Could you?
Okay. Okay. Z of H is just a standard notation. Z of H is called the center of H, or the set of all elements in H which commutes with everything else in H. So any group G. So definition. given a group G, center of G denoted ZG is simply those elements of G such that G prime equals G prime G for all G prime belonging to G. So I'm not saying, if the group is abelian, say if G is abelian, then ZG is G itself, right? And the minimal thing that ZG must have is that ZG must have what? There's one element in every group which commutes with every element. Identity. So ZG has to have the identity, right? But could have more. So ZG is now. Can you, of course, before we go any further, since you may not have seen this group before, this new group, you should prove that ZG is a subgroup. So I'm taking a break from proving the theorem right now. I'm just going back and filling in the blanks here. ZG is a subgroup. How do you prove that? The easiest way to prove something is a subgroup is?
Closure.
No. You take, if H1, H2 belongs to ZG, then prove that H1, H2 inverse belongs to ZG, right? That's the easiest way to do that. Right? Closure alone will not. Do you remember this theorem? Yes or no?
Yes, sir.
There's a theorem about general subgroups, the way to prove that something is a subgroup. So, of course, before that, what you need to show is really that if H, oops, that's what I was afraid of, something. Of course, if HG equals GH for all G belonging to capital G, this also implies that H inverse G has to be GH inverse, right? Is it okay? And then is a result which follows nearly trivially from that. I will leave you to fill in the gaps here, but this essentially proves that ZG is a subgroup of G. So it's not just a subset; it's a subgroup. In fact, it's more in the sense that it's a normal subgroup. So how do you prove that? Can we prove that this is a normal subgroup? In other words, we have to show that G, oops. Is this at all correct? That's something we need to check. Okay, so this is your homework. Check, is ZG a normal subgroup of G? I'm not saying either yes or no, it's something which you should check out. But the center is an important subgroup which a group has. Okay? So coming back to our theorem, remember that any ZG, this must be a subset of ZG, right? For any group. So what we are demanding here is ZH is only E, nothing else. So the only element in H which commutes with everything in H, remember I'm not even saying commutes with everything in E, but which commutes with everything in H is the identity and the identity alone. So you have to have this additional property before you can claim that N and H form factors in this semi-direct product, which will give you G. So the question, of course, is when we define the semi-direct product, we did not define it between just two subgroups. We defined it between G, capital G, which is the group, and a curly G, which remember was a subgroup of OUT G. Here we have N, a normal subgroup, and H just a subgroup. With this additional property, the center of H is just the identity. So how does anybody go from this thing here, H, to this thing? You need a set of automorphisms, right, of G. So how do we get that? Or automorphisms of N at least. So everybody knows what inner and outer automorphisms are? Yes? No?
Sir, I don't know what outer automorphism is.
You know what an inner automorphism is, right? That's all we really need today.
Yes.
Everybody else? Anybody here who doesn't know what an inner automorphism is? Everybody knows what an inner automorphism is, right? So, IH defined by G maps to H, G, H inverse. Right? So the set curly IH is the set of all inner automorphisms on the group G induced by elements of the subgroup capital H. Okay? And what is this inner automorphism? Inner automorphism is simply something which takes a group element to its conjugate element, HGH inverse. Everybody is sure that you know why this is an automorphism and so on, right? Again, I hope everybody knows this. And then also show, this is a homework where I am giving you the answer. In the previous case, I didn't really give you the answer. I don't really know whether the center of a group is a normal subgroup of a group or not. But I do know this one result. That the set of all inner automorphisms of, sorry, this is wrong. Set of all inner automorphisms of the group G is a normal subgroup of the automorphisms group of G. This is pretty easy to prove. Try it out. Now, can anybody tell me that given the group H, okay, we had this normal subgroup N, we had the subgroup H, what I need is for the semi-direct product result, what I really need is a set of automorphisms which will act on M. And this, of course, plays a pretty good role here, right? But can anybody tell me why I demanded that ZH has to be equal to E? Now that you know what role H is going to play, H is essentially going to come into the picture in the form of the inner automorphisms which H produces. Can anybody tell me why this is an important condition to have?
Sir, otherwise it will, if it's the center, then center means that GG prime equal to G prime G, so it will commute. So we are doing an automorphism, so it's H and H inverse. And if H has a non-trivial center, then H inverse can change places with N, and then basically H inverse become identity. So it becomes the trivial automorphism.
Yeah, but what's wrong with being the trivial automorphism? It might be the trivial automorphism, but why is that? That's good. That's a good point, really. But why is that a problem? If an automorphism becomes a trivial automorphism, why should that bother you? Or, of course, you will not know the answer to this until and unless I tell you what we are trying to do with this here. But let me just point out that what we want to say is that G is a semi-detached product of N and H. And you know that that's absurd, right? For a semi-detached product, you need a normal in a group. You need a group, and you need a set of automorphisms, a group of automorphisms, not another subgroup. But you should realize what we are saying here. We are saying that instead of H, we could just as well use IH. But why? Remember the connection between the set or the group H and the group IH is that every H can map onto a corresponding inner automorphism, right? Can you show that this is a homomorphism? In other words, what you are claiming is the map which maps, forget the H here, this could be any group. The map from the group to the sort of inner automorphisms of that group, which simply associates every element of H to the corresponding inner automorphism. We are claiming that this is a homomorphism. In other words, H1, H2 will map to I, H1, H2. How do you show that? It's straightforward. This is what H1, H2 of course will map into IH1, H2, that's trivial, but that's IH1 times IH2. That's what we need to show. But what is IH1, H2? IH1, H2 acting on a group element gives you this. But that's H1, H2G, H2 inverse, H1 inverse, right? So what is that? This H1, IH2G, H1 inverse, right? And that's IH1 acting on IH2G. Okay, so this is a homomorphism. This has nothing to do with the center or anything. But if ZG has a trivial center, only a trivial center, what happens is that this homomorphism becomes an isomorphism. Why? Why does that happen? Remember, the map is H maps to IH, right? What is the kernel of the map?
So in this, the entire center becomes the map.
The center is the kernel of this map, right? Because basically, if H belongs to ZH, then what happens is IH is simply identity, the identity automorphism, right? Is it okay? Because as you said a while ago, if something belongs to a center, it can jump across any element, and the H and the H inverse will just cancel each other out. So whatever G you start with, you will get G back. So that's what identity does, right? So kernel of this particular map that we're talking about is really the center of H. And by the way, what did I prove here right now? Actually, we did not prove that the kernel is the center. What we proved is the center has to be a subset, at least, of the kernel. Every element in the center has to be in the kernel. It will take a slight bit of extra care to prove that the center is the kernel. Right? But we just proved that if something belongs to a center and you try to define an inner automorphism using that element, you must get the identity. So every element of the kernel every element of the center has to belong to the kernel. But we have to also show that every element of the kernel has to be in the center. And that also is very easy to show. So I'm not going to do it myself, work it out. That's ZH is the kernel of this map, which means if ZH is the identity and identity alone, that's the isomorphism theorem proves for us that then this map is an isomorphism. This is clear to everybody. So the whole point of having ZH of this demand that we made, ZH equals E, is that this implies that so although we are saying n semi-direct product H, what we really mean in the definition is these two groups being isomorphic to each other, H and IH, we can use them interchangeably in this language. Is this okay? So that simply means now that what we can do is we want to define a map. Sorry, this is the wrong arrow. First, I want to define a map phi, which takes you from G and we want to show that this map will be an isomorphism. And what map are we going to define? We are going to define this map to be G maps into So do you realize that we are actually using quite a lot of results that we had already proven in the last proof? When I define a map like this, you must realize that I can do that only because given that capital G is NH and N intersection H is the identity which is a part of the demand, then G equals NH uniquely. This simply says that you can write G as NH. Okay? But in addition to that, once you have this extra condition that N intersection H is the identity, then G equals NH uniquely defines N and H, or the pair NH or the pair NIH. Is this clear? Okay, since there's no response, I'm assuming it is. So all you need to show now is that this is this map G maps to and then you're done. So you need to prove this. The proof is very similar to the proof that we did in the last case. Okay, so in both cases, really the tricky part is to establish that you actually have found a well-defined map. Once you've got the well-defined map proving that this is really an isomorphism, that's the easy part. So I will let you worry about this. We will discuss this again in the next session. If there's any difficulty, there should not be. Okay. So is this part clear? This is the kind of abstract. This is almost all about the kind of abstract group theory that we need to talk about. We are now going to go over to representation theory. So before that, if there is any question, please ask. So there are no questions? Okay, that's great. So do you have any questions from abstract group theory at all? Irrespective of whether we have talked about that or not. If that's not going to be relevant to what we are going to say, I'm just going to say we are not going to talk about that. But other than that, okay, let me just check one thing. I still am in the class, right?
Yes.
Okay. I suddenly felt that I might be just speaking to myself and there's nobody else on the other side. Okay, fine. So now we are going to take a look at what is actually the real goal of doing group theory in physics. Oops. Which essentially is the theory of representations. Just hold on, somebody is... Okay. So in mathematics, of course, when we define a group in terms of certain abstract objects, such as transformations or mappings, having a certain law of composition, which is also typically abstract. Okay. However, in physics, what we really are interested in are concrete things. And the reason why we are at all interested in group theory in physics is that a group may be associated with a set of concrete operators or functions which have a concrete law of composition which could be physically useful. Okay. So we will talk about representations of the group. This is essentially what a representation of a group is, a set of concrete objects which have the same algebra as the group. And although it's possible to discuss nonlinear representations as well, they turn out to be much less useful than linear representations. It's our luck that the easy version, that is linear representation, is actually the one which is most useful in physics. So we are primarily going to talk about linear representations. And we are going to talk about specifically the kind that we will need most often, operator representations. Or function representations. So let's start with operator representations. An operator here, of course, is a linear operator. So what in order to define that, we need a vector space. So we start with this. Let V be a vector space. Now there's a natural groups associated with any vector space. It is we take set of all non-singular linear operators. Oops. What did I manage to do? Yeah. On V of course, when I say form a group, then I have to specify two things. What are the elements? Here the elements are all the non-singular linear operators. I also need to specify what is the composition rule. And here the composition rule is something which you all know. You just do one after the other, right? That's what composition rule for operators is. You just apply one operator, then you apply another operator. Okay? So by the way, this group is actually called GLV, right? The general linear group of linear operators acting on the vector space V. More specific examples of this are, of course, GLNR or GLNC, where the underlying vector space is R to the N or C to the N or things like that. Okay. Then specifically, L acting on a group element G represents the element small g. Note that here we are not defining this representation to be mapped to be an isomorphism. We are demanding that this be a homomorphism. That is, of course, here G1, G2 is a product using the abstract group product, and this LG1 times LG2, this product is of course the product of operators, that is, do one transformation after another. So one kind of representation happens to be very, very useful, which is called the faithful representation, where if L is also 1-to-1. So if L is also 1-to-1, we say the representation is faithful. So at least linear group representations are actually quite useful things. And just hold on, this is the problem of taking a class in the outer room. I have to go and open the door for somebody. Just hold on. এখন তো ওদিকেই পাওয়া হয়েছিল তারপর আমি গাড়ি এখন এই সময় আছে ওর হয়ে গেছে okay, before I go on talking about this thing, let me just ask you people, we have already covered this, right? In the fifth semester? All this stuff? Definition of representations, say representations in on function space, all this? Have we? Come on, yes or no? Is somebody trying to answer and I'm not hearing you, or? No, everybody is nicely muted. I hope everybody has not gone to sleep.
Sir, as far as I can remember, you didn't do the function space representation.
I did do matrix representations, operator representations, stuff like that.
Yes, but it would be better if you cover them again. I mean, I actually forgot many of the things.
Okay. Fine. As well, I have no.
Sir, if you
I have no problem, except that if I'm completely boring you with stuff which you already know, it's better to move on to something else. So Ritik, you were saying something?
No, sir, I was saying the same thing. Like you didn't got the function.
You were saying the same thing that I'm boring you.
No, no, not that you didn't cover the function space representation.
Okay, that's why I didn't really cover. Okay, fine. Or maybe I didn't call it the function space representation. I may have covered it at least at that time. I don't know. I will have to check. Or I can't check. You will have to check when I talk about it now. Okay, let's go in order then. As long as I'm not completely boring you people. Okay. So we right now say that given a group, you can sometimes find a representation group on a vector space by operators acting on the vector space. So of course, you all know that the moment you have operators acting on a vector space, especially if the vector space is finite dimensional, then we can choose a basis on the vector space and we get matrices, right? Automatically. So we can immediately get matrix representations. And how do we arrive at matrix representations? What we do is we start with an operator representation. So for any given G, there is an LG, an operator acting on the vector space V, which represents the group element. And then what we do is we choose a basis E1, E2, En. That's a choice of basis. And the basis really is not a set, it's a tuple, right? It's an ordered basis that we are talking about here. And then just, oops, my battery is low. I thought I had connected the, oh, yes, that's coming. Yeah. I've taken a great deal of care to connect my power supply, but I forgot that my charger has to be connected internally, that it comes in two pieces. Okay, so what I do next is I apply LG on E1, E2, En in general on any EI. And this is the part which I'm pretty sure I covered in great detail before. This of course is, LG is a linear operator. It acts on a vector to produce another vector. So LG acting on EI must produce a vector. And because E1, E2 En is a basis, then LG acting on EI must be something and expand in terms of E1, E2, En. And so you can get numbers in front. And what I definitely covered in great detail is that this is DJI. That's the way we write this down. This, of course, is something which is very standard in linear algebra. This is exactly how you define a matrix representation for a given linear operator. The only tricky thing is we don't do it as Dij, we have Dji. And you know why? Because if you have this, then LG1, G2, EI, which is of course LG1, LG2, EI, will be LG1 acting on, sorry, this is an I, right? So J equals 1 to N, Dji P2, Dj, and then LGI goes and acts on that. But LGI, being a linear operator, can just safely jump across all these numbers here and will go and hit upon EJ. So what you get is these numbers will simply stay as they are. LG1 will go and hit EJ, and if you follow the same pattern as before, and this is K equals 1 to N again, D, EK and KJ here, G1. So then comes the rather fancy trick of interchanging the two sums, doing the K equal to 1 to N sum later, doing the J equal to 1 to N sum first. And here, of course, what you do is write this as Kj G1, Ji G2, Ek, and the upshot of all this, oops, this one, thanks. The upshot of all this is ultimately D of G1, G2 boils down to dg1, dg2. I hope you realize that here you really have dkj g1 later, right? It's in the second slot because g1 is going to act afterwards. So you can move it to the front and write this as a matrix multiplication specifically because you use this inverted order. If you had used the correct order, or what seemed like the correct order, dij, then you would have ended up here with djk g1, dij g2, which is not matrix multiplication rule anyway, right? So this is how you end up with matrices. So the matrix is dg. So given a G, we had a linear operator, that's a linear representation, and using a matrix, this matrix, once you have chosen a basis, this gives rise to matrices. N by N matrices which stand for the group elements G. And these automatically form a representation. So just let's try to figure out an example which may be of use for us in a physical context soon. So I will try doing something. Okay, I don't even know how all these things work, but let's see. Draw lines. So I'm going to try to draw an equilateral triangle for you. Something which looks somewhat like an equilateral triangle. I hope this is a decent enough approximation to that. And we have a set of 6 operations which keeps this equilateral triangle unchanged. I'm pretty sure many of you remember what we were talking about here, right? The set of 6 operations, of course, the ones I'm talking about is E, the identity. A, B, C are reflections in the 3 medians, and then there are 2 rotations, D and F. So this one is a 120-degree clockwise rotation, this is a 240-degree clockwise rotation. Of course, there's also a 360-degree clockwise rotation, but that's nothing but E itself. Okay? So this may be one median. This may be another one of the equilateral triangle. Of course, my triangle is hardly equilateral, but this is a 3rd median. And we have reflections in the 3 median. So we call, so reflection in this median we will call A, this one we will call B, this one we will call C. So this is really the vertex A, the vertex B, and the vertex C. So what we want to do is figure out a operator representation of this group EABC formed by EABCDF, which is essentially a group of 6 elements which happens to be isomorphic to the set of 6 permutations of 3 objects. So that's what S3 is. Sn in general is a set of permutations of n objects. So Sn is an n factorial order group. S3 happens to be a 6 order group which is isomorphic to this particular group EABCDF. Now, what we want to do is figure out a representation of S3, a matrix representation of S3. Why do we know that we can find a matrix representation of S3 here? Basically because we know that all the elements of S3 leave the plane R2 unchanged, right? You do identity to the plane R2, it of course stays unchanged. If you do A, some elements of R2 move to some other elements, but the plane as a whole stays unchanged. So does B, so does C, so does D, so does F. Right? So the plane stays unchanged under the action of all of these. So the plane furnishes, and here when I say action, I mean I actually do the reflections or do the rotations and whatsoever. But now what we want to do is find a matrix representation for this. So let's say, let me change the color of the. So we have to choose some basis vectors first. So this is my basis vector E1, this is E2. So what does E do to E1? Of course, it leaves E1 the same. What does it do to E2? It leaves E2 to the same. So E1 and this E1, of course, this is trivial. I don't really need to write anything down here. DE, of course, has to be what the matrix representation for identity always is. It's just 1, 0, 0, 1. Let's try doing something a bit non-trivial. Let's say B. Let's find out what does it do to E1 and E2. Or let's start with not B. Let's start with the easier one. Easier one for us is, of course, A. So what does A do to E1? A, remember, is a reflection in the vertical median. What does A do to E1? Answer.
Minus E1.
Minus E1. That's of course minus 1 times E1 plus 0 times E2. And what does it do to E2?
Same.
It keeps it E2, right? So that's 0 times E1 plus 1 times E2. So what's the matrix? What I will do Here remember what I will do is take these two coefficients -1 and 0 and put them down the column, first column, and take the coefficients for E2, whatever E2 becomes. In this case, E2 stays E2. The coefficients are 0 and 1, and I will put them down the second column. Of course, in this case, the extra care was not really necessary because what we had here is a symmetric matrix. But in general, matrices will not be symmetric, so you may have other things to play with, right? So you will have to be careful about the order in general. Let's do one thing. Since I want to keep the picture intact, let me just erase what I did with A quickly. And D, of course, identity is trivial to write, so let's not bother too much about that. Let's figure out what so dB will be. That's slightly non-trivial. So anybody tell me what dB will be? So first of all, what will E1 become under the map? Reflection in the median B. So which direction will the reflection point in? It will of course no longer be either in E1 or E2 direction. But what angle? Okay, can you say what angle it will make to E1 after reflection in B? What angle does E1 make with the median B in the first place? Yeah. What angle does the median make with E1? It of course becomes something which we can call E1 prime, but we need to expand this out in E1, E2. So what angle does this vector make with E1 now? For that, all you need to know is what angle does the median in which you're reflecting make with E1 and double that angle, right? What angle does the median make with E1? Quickly, this is easy.
$30.
30 degrees, right? That's the angle between the median and E1. So the angle between the reflected vector E1 prime and E1 is 60 degrees, right? So E1 prime is going to make a 60-degree angle with E1, so that has to be cos 60 degrees sitting here, half E1, plus, and that's sort of obvious, sine 60 degree, right? What about E2? E2 becomes E2 prime, which, by the way, you can figure out by saying E2 made an angle 60 degree with B, so after reflection is going to make an angle of 120 degree with the original E2, and you can use sine and cosine again. But the other way to do it is you would simply realize that after the reflection, whatever you are going to get, before the reflection the two vectors were perpendicular. After the reflection again the two vectors will be perpendicular, right? And this is simply what you're going to get, root 3 by 2. So the matrix DB, I hope everybody is clear about what I did here, how I could write down one from the other. This is not a great piece of mathematics, but these are the tricks which you have to know in order to do this properly. Right, so this is what DB is. Half root 3 by 2 down, root 3 by 2 minus half. By the way, this particular matrix representation is going to play a rather big role in one of the applications at least that we are going to do, which is at least discuss rather completely all possible modes of vibration of a equilateral triangle shaped molecule, in which we are going to need all these matrices explicitly. But I'm not going to bother working out all of them, but this is sort of straightforward, right? By the way, what is the determinant of this matrix? Come on. You can see what the determinant is, right? It's right there in front of you.
-1.
-1, and that shouldn't come as a surprise. It's a reflection after all, right? Reflections of determinants of -1, and the rotations which are E, D, and F will end up having determinants of +1. But that brings us to one important result which is actually quite useful, despite being rather trivial, which is once you have a matrix representation of any group, you can immediately reduce that to a one-dimensional representation just by taking determinants of every one of the matrices. Why does this work? It works because G1, G2 will of course map to DG1 times DG2. But if you take the determinant of DG1 times DG2, you get determinant of DG1 times determinant of DG2. So determinant of the matrix representation also obeys the same kind of multiplication rule. So you get a one-dimensional representation just by numbers, and for that particular representation here, E, A, B, C, D, F will be represented respectively by the numbers +1, -1, -1, -1, +1, +1. And if you multiply any two elements, say A and B, get two -1s in the representation, of course that goes to show that the product has to be a rotation, but we already know that, right? Two reflections, one after the other, has to be a rotation. This should be familiar to all of you, right? So given a representation, a matrix representation of whatever order, you can always immediately go from there and get a one-dimensional representation simply by taking the determinant. So that's one quick way of getting 1D representations. Of course, it might so happen that all the determinants are trivially 1, in which case, of course, you get a representation. Representing every group element by 1 is, of course, a perfectly good representation. It's not a faithful representation, of course, but neither then is this one which we talked about. 1 -1 -1 1 1 is not faithful because you just have two elements, 1 and -1, representing 6 elements here. It's not a 1-to-1 map. So even if your original map that you're talking about was faithful, in this case, so the map in 2D space that we are talking about is faithful, the 1D map that you get, 1D representation that you get may very well not be faithful. But it's a representation, it's actually quite an important representation. So what we have covered is we have covered linear representations and which are essentially representations by linear operators on a vector space, and we have covered matrix representations. Now in physics, very often what we deal with really are matrix representations. So it might seem that it's a waste of time to talk about linear representations in general on abstract vector spaces and so on. But it turns out that many of the results that we are going to talk about are way easier to derive in the language of abstract linear algebra than in the language of matrix theory. Matrix theory may give you more elementary proofs. Elementary does not mean simpler. Elementary simply means that it uses steps which are not of an advanced nature, does not use advanced mathematics in the steps. It just uses matrix algebra and rules of that. However, many of the results that we need, like orthogonality theorem and the projection theorem, which I'm pretty sure we did not cover last time. Orthogonality theorem I definitely did. Projection I don't think I covered. All these results are actually much easier to state or derive in the abstract linear algebra language, and from there we go on to use them. Once we have derived them, we can of course use them in the matrix language as well. So now what we are going to talk about is the other kind of representation which is very, very important in physics: function space representations. So here we start with the vector space. On it. Okay. Now, before we go any further, I'm saying linear space of functions. The order here is very, very important. Linear space of functions is not the same thing as space of linear functions. I hope everybody understands that. Of course, since there's no reply, I assume everybody does. So every element of this space F, so F belongs to capital F, implies F is a map from V to R, or C as the case may be. Okay? Now, what does this linear space of functions mean? What is the linear adjective here doing here? This is any function from V to R, right? Doesn't have to be a linear function. So when I say linear space of functions, what do I mean? By the way, what is the space of linear functions of F to, from V to R called? Everybody knows that, right? The space of linear functions from V to R, where V is a vector space. What is that space called?
A dual space.
That's a dual space, right? We are not talking about that here. Dual space is specifically manned by functions which are linear. Okay? Here we are making no such restriction. The function is a function acting on a vector space, elements of a vector space. Just hold on. Hi, Bipul. পিজি হসপিটালে আছেন, হ্যাঁ তা আছে। এখন যাচ্ছি কিনা আমি যাই না ঠিক, মানে করোনা টরোনার ব্যাপারে তো। আচ্ছা আচ্ছা, হুম 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 হুম। Okay, just hold on. There's a bit of an emergency. I have to give a number to somebody. Okay, so I'm done with that. Just call and confirm. হ্যাঁ তোমাকে হোয়াটসঅ্যাপ করে দিয়েছি এখানে আচ্ছা আচ্ছা ঠিক আছে ঠিক আছে ঠিক আছে তুমি একটুখানি কথা বলে দাও যদি আমি পরে কথা বলছি হ্যাঁ ক্লাসে নিয়ে Okay, so where were we? I think I can recall where we were from this. Okay, so we were talking about linear space of functions. What does this mean? It simply means, oops. Hi, Shubhadeep. ওটা তো আমি অলরেডি ওটা কাদের তোমার সিএসআই না ইনস্টিটিউটে আমার যতদূর মনে হয় আমি অলরেডি অফিসে পাঠিয়ে দিয়েছি না হয় তোমায় পাঠিয়ে দিচ্ছি কালকে কখন করেছি কাল কখন করেছিল মানে বিকেলে যদি করে থাকো তাহলে ঠিক আছে সন্ধ্যা করলে হয়তো পাঠাইনি ঠিক আছে এনিওয়ে আমি দেখে পাঠিয়ে দিচ্ছি ঠিক আছে একটু পরে আর আধ ঘন্টা পরে ওকে So that's the trouble of doing the stupid stuff which is called headship. Anyway, coming back to this, why did I say this is a linear space of functions? Because we can define addition of functions and we can define multiplication of functions by a scalar. How do you define this? Simply by saying f1 plus f2 is a function which acting on an argument x gives you f1x plus f2x. Similarly, how do you define alpha f? Where alpha is either a real number or a complex number depending on which kind of map you're talking about. Alpha f acting on x is simply alpha times fx. এই ক্লাসে আছে একটু পরে করছি Okay, so this is what makes the space of all functions, this capital F set, a linear vector space. So that's what we mean when we say linear space of functions. We don't mean that the functions are linear, but we just define that there is a linear structure defined on the functions. That is, we can add the functions, we can multiply them by scalars, and so they form a vector space of their own. Okay. So notice that this linear space of functions has V as its domain, and so since V is a vector space, what we are going to really say here is this. So let me just pull this up a bit. Yeah. So this is our central result, that given the space V, which is a linear vector space, it has non-singular linear operators acting on it. And corresponding to every such non-singular linear operator, there is a non-singular linear operator. Of course, I didn't say linear, but that's always what we mean. Linear operator acting on F. And this, by the way, has nothing to do with group representations. This is a general result in vector space theory. Okay? But once you have that, this immediately shows us how we can go from a set of operators. Say if I have a set of operators acting on a vector space furnishing a representation of a group, that is, simply these operators obey LG1, G2 is LG1, LG2. If we manage to cleverly enough define the corresponding linear operator on F corresponding to LG1 and LG2, we may hope to get a representation on capital F. So from a representation on a vector space, we can end up getting a representation on the space of functions acting on the vector space. And why is that important? Because very often in physics we deal with functions on a vector space. Things like, say, even the wave function, say in R3 is of course a function on a vector space. There's this R3 and there's psi of R3, psi which acts on R3 and produces a complex number, right? So it's a function from the vector space R3 to C. So if we have operators which act on R3 or really acts on physical space, but we have a representation of those operators on R3, we can use this prescription to translate that to representation of the same group on the space of functions, or in this case the space of all wave functions, which of course will be a very nice thing to have. Then you will be able to say, okay, the group elements do this to our wave function. Okay, and since the group elements have this property that G1, G2 does something which G1 and G2 does separately, done one after the other, that will put automatically a lot of restrictions on the kind of wave functions you can have, and those symmetry properties will be very important in studying properties of quantum mechanics. So this is exactly how quantum group theory comes into being in quantum mechanics. Space of all wave functions, or later on you will see space of all general kits, also furnish a representation of a group often, and you can use the representation theory of groups in abstract to actually study about the properties of the wave functions. But all this of course will work only if what I have written down right now is correct. That is, corresponding to every non-singular linear operator on V, we have a corresponding non-singular linear operator on F, and that correspondence is a useful one. So let's see how this works. So let T be a non-singular operator, which of course is nothing but a linear transformation on V. Define OT, given for every T, given OT which acts on F by, so OT acts on the set of all functions on V. That means OT of course will act on a function. So I will tell you what OT does to a function F. So acting on F, it will produce a new function OTF. Now how do we define OTF? How do we define a function anyway? Okay, I'm asking a question, so I need an answer. How do I define a function? Again, I hope everybody has not gone to sleep. Has everybody gone to sleep?
Sir, by explicitly saying how the saying what is
the
range, and then what is the domain and what is the range, and how it is being mapped. The elements.
Yeah, but here domain etc. is already specified. Domain and range are both specified, because if We are saying OTF is an OT acts on F to produce an element of capital F. That means it has to be a function which acts on the vector space V to produce an element either in R or C, as the case may be. Right, so domain range we already know here. You're right. In general, what we have to do is specify the domain and the range. But here the domain and the range are already given. So the other part of what you said is important, which is I need to specify exactly what OTF, the function, does on V for any V belonging to the vector space. Okay. Remember, we already know what F does to V, and we know what the transformation T does to V, right? But what we need to do is now, using those factors, we need to define this quantity OTF, this new function, which acts on V to produce a number. And the definition that we use, okay, this is a definition. So, being a definition, you can't really argue with it, but you can of course ask why, what good it is. The definition that we use is this. So OTF, the new function, acting on the vector V, is the same as the old function F, the original function F, acting on T inverse V. So this is how you define this. Okay, this is of course true for any function F. So for any function small f, you get a new function OTF by following this rule. So question, why do we have a rule which looks this crazy? Any answers? Why should we want to have a rule? Of course, notice that we have a function and we want to get a new function. That much we have to do, which means the original function acted on vectors to give you numbers. This new function OTF has to act on V to give you a number. On that grounds, it is fine. F acting on T inverse V is a number, right? T inverse V is a vector. So F acting on that is a number. But why do it that way? Why not say use F of TV? That could be at least equally obvious choice. So take V, act on that by T, you get a new vector, you apply the function F on that, you get a number. You're done. That's your new function. That's the value of your new function acting on V. Why not? So the question really is, you have to prove that this particular definition has some added advantages. Of course, you should not really argue with the definition. A definition, after all, is just a name, so you can't really argue with the definition per se, but you can, of course, ask whether this definition is at all useful or not. Okay? So let's check whether it's useful. So first of all, there are several claims that I made about this OT map, right? OT is a non-singular linear map on F. That was a claim. Before we ask about why T inverse and why not T, at least let's try to establish that this is really a non-singular linear map. So how do we go about doing that? Of course, to check, so there are several things to check. First of all, is it linear at all? Linear means this: when OT goes and acts on alpha 1 F1 plus alpha 2 F2, this is what a linear combination of two functions is. Does it give you the linear combination of OT F1 and OT F2? Of course, to figure that out, what you need to do is apply this whole function on an arbitrary vector V and check what comes out. What comes out according to definition is simply alpha 1 F1 plus alpha 2 F2 acting on T inverse V. And then that is equal to alpha 1 times F1 acting on T inverse V Okay, in the first step we used our definition of the map OT. In the next step, all we have done is we have used our definition of what alpha 1 F1 plus alpha 2 F2 means. And now this is simply OTF1 acting on V plus alpha 2 OTF2 acting on V. So what we have, sorry again, since I'm using this almost for the first time, so making a mess of things from time to time, but anyway. And since this is true, so I've used the definition of linearity of functions twice. Once when I broke this up, and then when I put this back together to this. But now since this is true for all V, then it has to be, if it's true for all V, then you must have OT alpha 1 F1 is alpha 1 OT F1 plus alpha 2 OT F2. Right? So linearity is established. That's fine. What about single? Say, what about non-singular? So to show that it's non-singular, what does non-singular really mean? In the context of linear vector spaces, what does it mean when you say an operator is non-singular?
Sir, do we show that there exists an inverse?
You don't have to. To show non-singular, what's the easiest thing to do?
Determinant?
The determinant, of course, is not easy at all. First of all, determinant is not a very natural thing for linear operators. Determinant, you can define determinant for linear operators, but for that you have to go via basis choice. Once you have made a basis choice, you get a matrix, you find a determinant of that. What, of course, and why you can call it a determinant of the linear operator and not just determinant of the matrix is that no matter which basis you choose, you end up with the same value for the determinant. That's why you can associate a determinant with a linear operator, but the calculation of that is pretty non-trivial. Just hold on. Yeah, hi Asha. So the question I have for you is this: what is the easiest way to establish that a linear operator, note linear operator, is non-singular?
The only vector it takes to zero vector is the zero vector.
Exactly. That's the easiest way to prove this. So a singular operator takes non-zero vectors to the zero vector. Well, at the level of transformations or level of linear operators, the easiest way to check for singularity is this: does an operator take a non-zero vector to zero? If it does, then it's singular. If it doesn't, then it's non-singular. By the way, the proof of this is of course a theorem, but the proof of this theorem is very similar to the isomorphism theorem. In fact, it's essentially the same theorem in a slightly different language. That is, the theorem which says that the kernel of a homomorphism has to be trivial for it to qualify as an isomorphism is essentially the same theorem as the one which I'm quoting right now, and the proof goes very similar to each other. Okay? So now what we have to check is this OT is not, remember we have already stipulated that T is non-singular. We have started with a non-singular linear operator on the vector space capital V. We are asking, is OT, which is a linear operator as we have established right now, or it's a linear operator on capital F, the set of the space of all functions on capital V. Question is, how do I show it's non-singular? The answer is check this. But this is the zero function. If this implies that f equal to 0, then you are done. But what does it mean when you say OTF is a zero function? OTF acting on V is by definition f acting on T inverse V. Right? Now if OTF is 0, then acting on any V will be 0, which means F acting on T inverse V will be 0 for all V, right? Is it okay? But F acting on T inverse V is 0 for all V actually means F is 0 on all vectors, right? Can you see why? That's the basic result for non-singular vectors. Sorry. Okay, this one I can't really blame my tablet on. I have to blame my inability to do logic properly. Oops. So for any W, any vector in the vector space, you can find a V such that W is T inverse V. So f of W will be f of T inverse V, but f of T inverse V we have already seen is 0 for all V. So this means this would have implied that f of W is 0 for all W belonging to the vector space implies f is 0. So only function on which OT is going to give you the 0 function is the 0 function. So that's all you really need to prove, that OT is non-singular. Is that okay? So what we have done now is proven two parts of that claim. It's a linear operator on capital F is non-singular. So that's done. But would any of these have been hampered if we had defined OTF of V to be, let's call this O tilde T for the time being, because this is not the OT that we have defined. But if we have defined OT tilde F to be a new function whose value is f of TV, would our proof of linearity and the proof of non-singularity have gone through? Yes or no?
Sir, I have a question.
Yeah, go ahead.
In the proof of the non-singularity of OT, what did we use?
Sorry, I couldn't get you. After did we use, you cut off. Did we use?
Yeah, what did we use?
We use the fact that T is non-singular, which means that
so that we can define T inverse V and say that
so that we can claim that no matter what vector we choose, we can always find a V such that T inverse V is that vector.
Okay.
Yeah, but will that be hampered? Will the proof be hampered if we had used f of TV? All we are to show is that in that case there is for any W there is a V such that W is TV. But since T is non-singular, a non-singular linear operator is always invertible. So W equals TV, there is a V such that W is TV is trivial, isn't it? The two things that we have proved so far, linearity and non-singularity, both would have worked for this O tilde T function as well. So this map, we are talking about two different maps, OT and O tilde T. Defined differently, OT is the one which we are going to actually use. This is of course defined via this. But both OT and O tilde T are linear maps on capital F, and they're both non-singular maps on capital F. So linearity, non-singularity does not distinguish between the two. The reason why we choose this particular one, the second one, and not the top one, despite the fact that the second one, at the face of it, looks slightly crazy. Why f of T inverse V? Well, there are two ways of answering this. One is, this has a nice property which O tilde T does not have. The other is, even on physical grounds, the lower one is more preferable. Let me just try to explain that first. When I say on physical grounds, suppose I have a sphere on which there's a temperature distribution. Let's just say, that's an example I'm just picking up. I have a sphere, let's say the Earth, on which there's a temperature distribution. At every point there's a temperature. So this is a function. All of this frankly is a bad example, really strictly speaking, because a sphere of course is not a vector space. But the idea is sort of inherited from there. Well, if I do an operation, if I rotate, say, the sphere, every points move to new points. Not every point doesn't move to a new point. After all, the north and the south pole doesn't move points on the axis, but every point in general moves to a different point. Okay. So now I want to define a new function on the rotated sphere. So coordinates of every point is changed. Every point has become a new point. And so the temperature at every point has also changed. But what is the temperature at a point on the sphere now? It actually is the temperature that used to be at the point which was where, which was the one which was rotated into this. Sorry, is this language clear enough? See, I do a rotation.
If I am getting you correct, this analogy can also be applied to the transformation of scalar field under a Lorentz transformation.
Well, that's exactly, it's not an analogy, it's exactly what you do.
Yeah.
There's no analogy here. The reason why you do it for Lorentz field, Lorentz transformations and scalar fields is exactly this. That's a natural thing to do. Okay. What is the value of the, so the temperature is just an example. You could have said scalar, I could have just started out by saying scalar field on R4. Same thing would have gone through. The idea is, what is the value of the temperature in, suppose Paris has been rotated into London, let's say. What is the temperature of London after the rotation? So this new function which describes the temperature of the sphere of the Earth after the rotation will assign to London the temperature which used to be of Paris before the rotation. So to find out, okay, I want to find out the value of the function at London, I have to find out first which point used to be London. Paris used to be London before rotation. So now the original function must have given us the temperature of Paris. That's why the T inverse V comes in. Where did the point V come from? After the transformation T has applied, the point V, which is the point which is the point V now, used to be the point T inverse V, and you have borrowed the function value from there. So this is absolutely the natural thing to do in a physical scenario. When you say the function has changed, all you have to do is find out what the function used to be at the original point and just take that value. So that's a quote unquote physical justification. But this leads to a rather nice mathematical justification, which is this. Suppose I do two transformations one after the other, and this is exactly why this becomes important in group theory. Suppose I do OT1, T2. T1, T2 is of course doing T1 and T2 one after the other. So what is this? This by the definition that we have used is this. Okay. So that's f of T2 inverse. Okay. So for the time being, let's just think of T inverse V as a vector, some argument which I have applied here. So this is nothing but OT2F, the function, acting at the point T1 inverse V. Right? OT2F is a new function. What you get when you apply T2 on the vector space, in the function space, OT2 gets to act on F. But this, by definition, is OT1 acting on the function OT2F at V, which leads us to this result, this critically important result. The OT1 T2 is OT1 which actually means this, that the OTs, if the original operators T1, T2 furnish the representation of a group, the T1 corresponded to a group element G1, T2 corresponded to a group element G2, and so T1, T2 must have corresponded to G1, G2. OT1, OT2 will also correspond to G1, G2 in the same way. OT1, T2 will be the function group space representation of G1, G2. Is this clear? So this is the group theory perspective on this. Why we want the T inverse. Just to make it a bit clearer, if it's not yet, let's try to do this with O tilde. This thing acting on V will be what? It will be F. Sorry, it will be F acting on T1, T2V. So FT1, T2V, not a problem. And FT, what is FT1 acting on T2V? Is just nothing but O tilde T1 F, this function, acting on the argument T2V. So far so good. But that's nothing but O tilde T2 acting on O tilde T1, the new function, O tilde T1 F, the new function, giving rise to another function which will act on V. But that means O tilde T1 T2 works out to be O tilde T2 O tilde T1. Wrong order. Not what we want. Okay? So while both OT and O tilde T defines linear non-singular operators, okay, one of them, the one which we have chosen, has this advantage that if your original operators T1, T2, T3, etc. form a group representation, then OT1, OT2, OT3 will also form a representation of the same group on a different space, of course, on this vector space V. Is this clear now? Any questions about this? Is a tricky bit because very often the order of action of these things confuse people. So it's important to be very clear about this because this is the only tricky bit here. Everything else is sort of straightforward. With all that I've talked about today, this really is the only bit which can be a bit confusing. Because I may have been able to make everything confusing, but that's not the point. The point is this one is intrinsically confusing. It confuses a lot of people often. Although you go about it carefully, it's really pretty easy. So if you have any questions, I will of course fold up here today. But if you have any questions about this, please ask. None. Great. That means everything is clear or nothing is clear?
Sir?
Yeah.
Sir, yeah, the thing we just did, so basically what we have done is if we have a group G and we have, say, its representation on some linear vector space V, so
Yeah.
what we have done is basically found a representation on a different vector space F, which is the...
Yeah, which is derived out of the set of functions on V. Right. So this is basically getting new representations from old in a way.
Yeah.
But also but we are doing this not just for the heck of it, not just because we want to find new representations, but also because these new representations may very well represent physically interesting objects. Like, as I said, very clear, that was the most important part. Say the space of wave functions, for example, or space of physical, say even the space of all functions which describe temperatures, or some scalar fields, or why just stick to scalar fields, or other kinds of fields defined on a vector space. All these different things, you have to realize one thing, all these different things that we talk about, scalar fields, vector fields, tensor fields, all this, why are they so important? Basically because they all furnish representations of some kind of symmetry group or the other. And the way in which they do that is via this particular approach. That is really why all these things are so important in physics. So there is a unifying theme here, really, which we often miss because we study these things piecemeal. We study scalar fields and vector fields first time long before we ever learn anything about group theory and so on. Okay, so you have to understand that this instead of learning about these things piecemeal, if we learn about them in a unified structure, it will perhaps show you the unity of things. At the same time, we have to also realize that the reason why we don't study them all at the same time is because until and unless we have enough appreciation as to why these things are useful, putting in a lot of stuff can also be confusing. But by now, you have seen different kinds of mathematical entities being used in physics. I'm not saying it's always the case that you use a mathematical entity if there's some kind of group structure behind it. That's not really true. I can't be that much of an extremist. But most of the mathematical entities that are used in physics are used because there is some kind of symmetry in the underlying world which this particular structure is trying to capture, and group theory is behind that part. Okay, any further questions? Next day we are going to explicitly calculate a few function representations and show how to see how to get new representations out of old. Say, we might even start with this equilateral triangle thing. So I will ask you to all to do one thing. The 6 operations on the equilateral triangle, the 3 reflections and the 3 rotations. Find out the matrices for each one of them. So these will be 2-dimensional representations that you will get, right? But let me just point out that one thing you could do is something simple like this. Let's say, before we go, let's say the vector space there, of course, is R2, right? So it has elements x and y. But we can talk of functions on R2 which take x and y into, say it has all possible quadratics. So and what's the dimensionality of this space? All possible homogeneous quadratics. Of course, before you answer such a question, you should check whether there is a vector space at all. That is, if I add 2 homogeneous quadratics, do I get a homogeneous quadratic? If I multiply a homogeneous quadratic by a scalar, do I get a homogeneous quadratic, and so on. All these things you can easily check. But once we have done that, what is the dimensionality of this space? It's 3. You can see it's 3. It's easy to see, right? You have basically 3 independent vectors in this space: x squared, x, y, and y squared. Or looking at this from the other angle, you need 3 numbers to describe an arbitrary map here: A, B, and C. So this is a 3-dimensional space. So although our original space was 2-dimensional, this space of functions, this particular space of functions is 3-dimensional. And when we look at the representation of the group S3 on R2, which we found out, at least partly found out so far, we found out at least 2 or 3 of these matrices. 3 of these matrices. We need 3 more to go. From that, we can find out 3-dimensional representations by going by this particular function space of functions. And then, if we went to say homogeneous cubics, that will give you a few more terms. That will give you 4 actually, and so on. And you can find different representations, different spaces, and that should not come as a surprise. After all, if you look at the rotation group, that's a group which acts on 3 dimensions. So it acts on real world and it acts on the 3-dimensional world. Its most obvious representation is the 3-dimensional representation formed by the rotation matrices, the 3x3 matrices that we all know and love. But you can find representations of this in all dimensions, right? How do you find that? What kind of representations do we have of the rotation group in say 5 dimensions? Can you give me an example? A 5-dimensional representation of the rotation group? All of you know the answer, but yeah.
We did the representation of angular momentum algebra
Yeah, but can you? The trouble with doing an abstract representation is that sometimes it sort of hides from you the fact that it's also much simpler, or at least much better known. Not necessarily simpler, but at least something you know better. So all the L equal to 2 spherical harmonics, which you should know better than these represent, although you may not, but that's basically because you have not worked with spherical harmonics enough. But the 5 spherical harmonics corresponding to L equal to 2, these are special functions from the theta phi space, right? And they furnish a representation of the rotation group in 5 dimensions. Take the L equals 10 spherical harmonics. They furnish a representation of the rotation group in 21 dimensions. But they all do that via exactly the same route as the one we have talked about. You have a vector space on which your group is acting. So you know T, you know the operators T corresponding to your group elements G. You have a function, set of functions on that vector space. From that you just construct new representations on the space of functions. That's it. So this is actually something you have done all your life, by the way. It's just that we are formalizing it and using big words here. But whenever you have written down spherical harmonics, for example, you have actually done exactly the same thing with the rotation group. So we will do this explicitly on the next day, that is for some of these groups. So I would urge you to actually at least explicitly calculate all the 6 S3 matrices, matrices representing S3 on R2, the kind that we did so far. Okay? So let's call it a day today, but you have quite a few homework to do. Remember that. I'm just stopping the recording now. Okay, I can't stop the recording by clicking on the record button. I have to stop the recording by clicking on the stop record.